We are here tonight to talk about pandas with Anna. And first of all, thank you everybody for coming. Really glad to see such an awesome turnout for this presentation. And we have just a couple people who want to come up and talk about some of the upcoming events that are going on in Code and Supply next week. I think, are they both next week?
One of them's next week.
Okay, one of them's next week, and the other one is at a different time. I bet you'll find out in a few seconds. So first of all, I'm going to introduce Matt, he'll tell you what he's going to talk about.
Hi, welcome to Google Pittsburgh. I'm a software engineer here at Google, and on Tuesday of next week, Tuesday the 1st? Yeah. I'll be doing a talk on Go, conveniently located at the Uptown communal office thing where Code Supply is headquartered. So yeah, you should come out to it. It'll be fun. Welcome to Google Pittsburgh.
Awesome. And next we have Brian. I confirmed that with Justin a second ago too. Terrible memory.
Hey everybody, my name is Brian Cardell. I represent the JS Foundation, which formerly was jQuery Foundation for web standards. There's an effort underway. Actually, the first group of it here is in Pittsburgh, but it's a worldwide thing. It's in setting things up in London, France, Canada, all over the US. Lots of big orgs are behind the idea. It's about involving developers in the web, and our next thing is the 7th, and we're going to have a remote Q&A with Mark Nottingham, who is the chair of the HTTP working group in IETF and a member of W3C Technical Architecture Group. And then it is mostly discussion. If you want to look, we've had a couple of things already. They're on Code and Supply YouTube. The 7th, please come.
Awesome. Thank you very much. That also sounds great. Cool. So without further ado, I'm going to introduce Anna Filippova. Is that?
Ish.
Okay. Anna Phil, as you can see on her Twitter handle.
Underscore Phil. Anna Phil is someone else who takes very pretty pictures.
Yeah.
I was late to Twitter.
So yeah, we'll get started with that. So give her a round of applause.
I know, I got the projector working, so I think you can all, take a deep breath, go home. Job's done. Slides are up. Okay, so how many of you work with Python on a regular basis at work? Okay. Keep your hands up, keep your hands up. How many of you work with pandas every day? Nice. Okay, that's okay. How many of you work with big data type things with pandas? Things that don't run in memory? Okay. How many of you want to come and do a talk about that next Python meetup? Yeah? Okay. I saw that hand. Nick's going to come talk to you after that.
Pretty bad.
Okay. So hang on. Hi. I promised you cute things. So hi. As Nick said, I'm Anna. I came to Pandas not very long ago because I was working with, actually I should tell you who I am first, and then we'll get to that. So I work with different kinds of data. I'm a researcher at Carnegie Mellon, and I study people and how they interact when they're writing software. So I came to Pandas because I had a really interesting data set of a bunch of threaded conversational archives spanning a bunch of different years, and this seemed like a good way to do it. But I had lots and lots of questions when I started diving into it, so I thought someone else might have questions too. So the way that this talk is structured is kind of a very quick introduction to what this thing is. So a lot of that might be familiar to all of you who put your hands up, and I apologize. But for the rest of the folks, we're going to kind of briefly go through that. And then we're going to slowly try to dive deeper into more things that I know I promised you in the abstract. I kind of put everything but the kitchen sink in there, so we'll see how much we can get through. Okay? Okay, so just to clarify, we're talking about this pandas, not this panda, not these pandas, right? Okay, this one. But I'm gonna leave this one up here, just for you to take it in slowly. Cool. All right, everyone cool with that? Everyone in the right place? Awesome. All right, so my outline doesn't fit on the screen. That probably means it's too long. So we're gonna start by talking about definitions, and the reason for that is because when I started looking up what pandas is, I got a lot of really conflicting information. So I want to highlight that and kind of talk about some of those different ways that people have described the library. We'll talk a little bit about mental models, how to approach this thing, what is it like, what is it not like, what does it do similarly or differently from other things you might be familiar with, what are common data structures, and I want to talk a little bit about performance as well relative to some of these things. And hopefully we get through that relatively quickly, and then I'll just dive into examples with things that I promised you. So we'll start with simple things, basic operations, but then we'll look a little bit more into how to work with time series data, group by objects, indices, multi-indices, things like that. And like I said, we'll see how far we get. And actually the part that you don't see here, there's a little line that's supposed to be there that says Pandas version 0.19, which came out this October. Maybe we'll get there, let's see. Okay, so can you guys see this at the back? Ish? Okay. Somewhere, not here. Okay. If you need it, there are copies of these slides, so if at any point you want to look up something, I have a link somewhere here, let me find it. Probably need to refresh this, sorry. Nope, still not there. Because it's not a slide. There we go. Okay. So if at any point you want to look at something that you can't see really well, or if you want to follow along, all of this is on tinyurl.com/pandas-python-pgh, and it's available in a number of convenient formats, including .html, .py, and for those of us who love Jupyter notebooks, and a Jupyter notebook. So you can actually play with things and run them. Okay? All good? All right. Okay, so let's talk about what this thing is. If you Google pandas, you're going to get lots of pictures of pandas, but you'll also get a Wikipedia entry that tells you that there's this thing for Python that does data manipulation and analysis, and some data structures and operations, and it manipulates numerical tables and time series. And that's a pretty good definition, but it kind of only scratches the surface of what we're talking about. If you go to the GitHub page, then it will tell you it's a data analysis / manipulation library. And you're like, okay, well, is it both of those things? Which one of those is it? And then it compares it to our data frame objects, and it says that there's statistical functions in there, and you're thinking, cool, this thing sounds really awesome. And then you dig into the documentation, and it's like, oh, this is like a SQL table or an Excel spreadsheet. And then you kind of go, oh, okay, wait a minute. So a lot of things all kind of wrapped into one. And it reminded me of that parable of, the blind man and the elephant. They're kind of all describing a piece of the elephant, but each one of them is technically correct, but you have to put all the pieces together. So I'm going to try to do that a little bit. So excuse the crudity of this particular graphic. I'm not a graphic designer, and I did not have time to draw this to scale. Some of this might be to scale, some may not. So I was trying to represent here a bunch of different things that are often talked about in combination with the Pandas library, and point out how this might be similar or different to the library. So let's see. Let's start with NumPy. So Pandas is built on top of NumPy, if you didn't know that, and it utilizes heavily the capability of multi-dimensional arrays that NumPy does really, really efficiently. The difference is that NumPy only supports numerical information. So if you're trying to do anything that is non-numeric, it gets really, really slow, it gets really bogged down, it's not optimized for that. So Pandas takes that as a core and builds a whole bunch of things on top of it. There's also a whole bunch of different functions and abstractions that allow you to do all kinds of other things with data that we're going to talk about in a second. What NumPy offers over Pandas is a more direct interface with things like C and Fortran. So if you're interested in particular speed optimizations, then You can do some things like that with pandas. There's Python bindings that you can use. So if you're a particular speed junkie, then there's a link in the documents that I give you a link to for a reference. Or you could just Google pandas and Python and you'll go to the documentation, which is basically the link. Okay, so what about SQL? Pandas does a little bit of SQL-y type things, mainly simple joins and things like group by. Simple joins rather than all of the join functionality that you would expect in SQL. And what I mean by that is you won't be able to get things like join by this value if it is equal to something else. Pandas doesn't do that, and for good reason. Pandas does group by, in my opinion, more interestingly than SQL because you can do a lot of other things with those group by objects after you extract them. And we'll talk about that in a second too. But what you don't get with pandas that you get with SQL is a lot of stuff, like obviously storage. Pandas is in-memory manipulation. It is not a thing that stores data. You get conditional joins. You are able to operate on, again, this is SQL versus pandas. You are able to operate on things that don't fit in memory, and some might argue speed. A while ago, Wes McKinnon, the guy who did all the pandas library, actually compared the speed of pandas and some SQL operations with, I think, SQLite. And that's not an apples-to-apples comparison because one is, reading things from disk, one is doing things in memory. But the interesting thing about that was that it was kind of comparable. So pandas is really fast, but so is doing stuff in SQL. So depends on what you need, but they're kind of different beasts. Finally, R. And this is where that text gets a lot smaller and there's a lot more stuff going on over there. So at that intersection of pandas and R is a lot of overlap. A lot of concepts like data frames, some statistics. I say some because there's a whole world of other things out there that R offers that pandas doesn't. Visualization, rolling stats, missing data, apply map functionality, that sort of thing. And R, again, it's not a fair comparison. R is a huge ecosystem. Pandas is a library. Obviously, there's lots more things going on for R than there are for pandas. If you are on the bleeding edge and you need specific kinds of statistical tools, you're more likely to find them in R than you are. You're not going to find them in pandas. You're going to have to use other libraries like stats, model, or something in order to plug into that. All right. So, I know. I'm going to pause every time there's a GIF. It helps me catch my breath and also because they're adorable. All right, so let's talk a little bit about performance. And here I'm talking specifically about pandas versus R performance because it's really not fair to compare pandas versus numpy or pandas versus SQL. It's kind of not fair to compare pandas versus R, but we're going to do it anyway. Okay. And we're going to compare pandas versus a few specific R libraries that do pandas-like things. Okay, so a lot of things that I found online about performance for pandas were very, very old. Actually, let me go back a bit. Are very, very old. So there's things from like 2012, 2013, if you go online to like Stack Overflow, where people have these conversations and lots of numbers that are really, really out of date. And I was kind of wondering to what extent that's really true, because everyone is saying pandas is really fast, pandas is great for doing all kinds of things compared to all this other stuff. And Wes has spent a lot of time optimizing it. So let's see to what extent that's actually true. If you compare pandas and the zoo package in R, which does, if I remember correctly, and you can correct me if I'm wrong, time series related things. And in this particular benchmark, we're comparing how the speed of adding labeled vectors. So basically vectors of data which have some sort of either ordered or unordered labels. And pandas is either 12 times faster if that's unordered data, or if it's ordered data, it's up to 80 times faster than zoo. And these are recent statistics, I've just run them. And that's been consistent over the last few years. So that's a pretty big performance enhancement. Okay. There needs to be like a Hitchcock thriller kind of audio at the back. All right, okay. So the other thing that you might see, or you actually probably can't see because this is really small, is a conversation online about pandas versus doing joins in pandas versus R. And these benchmarks are also about circa 2012, and for basically pandas outperforms everything on orders of magnitude of like 5 to 25 times. Okay, so I thought, okay, let's run that again. And the truth is that it's a little bit more complex than that. So R has caught up somewhat to pandas, depending on what you use. So the built-in library that, the built-in tools that you might use to merge and perform joins in R is base merge, and that is like 12 to 15 times slower on one-to-many joins, and it is like 16 to 23 times slower on many-to-many joins. But if you are using things like data table is actually twice or 3 times as fast on some things, except outer joins, right? And the reasons for that are the different ways that indexing is performed. So data table does a lot of caching for you, and that can be a little bit slow if you're doing outer joins. Pandas is really efficient at working with things that aren't necessarily sorted beforehand or aren't necessarily indexed or cached beforehand. It does that really, really well. And the reason for that is because it's written partially in combination in Python, and it uses things like Caleb, which, if you go to their GitHub page, they will tell you they're one of the fastest implementations of things like hashes and a bunch of different data structures in all programming languages. You can test that claim yourselves if you like, but I'm going to move on. Okay, so one more element of mental models before we dive into some code, if that's okay. And the last thing that I want to share is the 3 different kinds of data structures that you would encounter if you're working with pandas. These are panels, data frames, and series. And they're interrelated. Yeah, okay. They're not distinct things, but they're actually nested ideas in pandas. So let's work through an example so you can see what I mean. This is a series object. What I'm doing here is I'm saying, okay, let's say I have a class of students. I have 3 students in my class because I don't want to type more. And I'm randomly assigning them scores from 1 to 10. They've taken a test, and that's my grading strategy. Great, you're paying attention. All right, so this is how you would create a series object. And that on its own is not very interesting, except that by default everything is indexed in pandas. So if I had not done this, if I take this away, whoops. Oh, of course. I need to actually run some code. You know, every time you do live coding in a presentation and you think it's gonna be fine, and then it's not. And I would know because this is my first time doing it. Okay, so if I had not included the indexes of 3 different kinds of students, then Pandas would index it for me and it would start with 0. Okay, so it will automatically index everything. It will also interpret a data type for you, depending on what you've given it. So in this case, I've given it 3 integers, and it's figured out that, oh, you've given me 3 integers. I'm going to make this an integer column. The cool thing about Pandas is that unlike numpy, it can have different types of data across different columns within the same object, and those are all fairly optimized in the way that you work with them. So Pandas is going to interpret all of that for you. The problem is that it does that every time you do a merge or a join or an append or something, and that can get a little bit slow. So try not to throw that at Pandas. And we're going to look at an example in a little bit. I'm going to put this back because we need it. All right. So there we go. Student scores for test number 1. That was a series object. All right. So what's a data frame? A data frame is a couple of series objects smooshed together. I wanted to use the word smooshed in a presentation for a while now. So let's say we have 2 different subjects, English and math. Okay, and now I have the same 3 students, student 1, 2, 3, taking a math test alongside an English test, and I'm going to randomly generate some scores for them too because I'm that kind of teacher. This time I'm going to do it from 10 to 20. So the maximum score for the math test is 20. And I can just throw, you can see my cursor, I can just throw both of those series in there into a dictionary object and pass that to Pandas, and it's going to know what to do. And it's going to give me a nice cute data frame here that I can then work with. I can also do this by just feeding in a list of values, so I don't necessarily have to pass a series object in order to create a data frame. So let's say I have these 2 data frames, And now I want to see, actually, what's going on here is these are the same subjects, same students, different semester. So let's say I have time series data now, and I want to compare student scores from semester 1 and semester 2 across the same subjects and across the same students. This is where the panel data structure is really, really useful. Okay, and that is basically folding in both of those data frames and turning it into a three-dimensional object, and that's how that looks. So we have, let's see if the pointer works. Oh, too far. All right, I'm gonna wave my cursor around. So we have data frame here, which was our first semester. And we had the second data frame where we randomly generate some more scores for the same students on the same subjects. And I do the same thing. I do from dict, because I'm basically feeding a dictionary into this. And there we go. I can pull up semester 1. I can pull up semester 2. And I can't because I haven't run that code. Going to be slow. All right, okay, so semester 1 and semester 2, slightly different scores, all right? You can also access the subjects themselves across different time periods, and then you would do a slightly different command. So instead of just specifying the square brackets the way that you'd normally access a column of data, you can just do minor_xs, and then you can do either English, which we see here, or you can do math, and you will get scores for both semesters. So that is a handy way of working with three-dimensional data, and especially if those are separated by time, that's kind of what this is built for. And it turns out that Python Pandas is actually named after panel data S. All right, so that concludes the mental model type stuff. So make sure we're all on the same page. All right, cool. So I'm going to start going through some quick examples, and it's going to get, it's going to start really basic imports, things like that, and we're going to get progressively more complex as we go along, and we'll see how far we get with the examples. Okay, let's say we wanted to import some data because we have just learned that Pandas doesn't actually store things for us. We have to actually get it from somewhere. So we can do CSVs, any type of flat files. We can do SQL databases with connectors. We can do HDF5 if you're a real speed junkie. And yes, you can also do Excel if you really, really want to. So let's say we have a couple of raw CSV files, which again, you can't see because this is really small, but trust me, it's just 2 columns. One is a year and month, and the other column is in one file, a representation of the monthly milk production per cow from 1960s onwards. And our second file is monthly CO2 levels, and our third file is the average rainfall per month in a section of the Amazon. Okay. And these all have year, month columns and a column for the value, basically 2 things. So let's look at how to import that. You would obviously run this thing, which I had earlier forgot, and we'll talk about what matplotlib inline is in a while. You basically need to throw this thing in there if you want to print stuff with Jupyter into this thing, which is why it's there, so we don't have to talk about it anymore. All right. And in this case, we want to specifically target the time series data that we have in our CSV files. So we can tell Pandas when importing that, okay, this column has time information in it, try and interpret that for me. So that's what the second line does, parse dates. So we give it a CSV milk, and we tell it parse the column month because that's what our column is labeled in the CSV file. We want to reset the column names in this example because the second column name is really long and I don't feel like typing that all the time. And in order to do that, you specify header 0. You can Google most of this, so I'm just going to kind of move really quickly through that. And we also specify the index column month, which is what we parse the dates for. And a note about this is that Pandas is going to try and interpret this for you. But obviously, that is not the fastest way to do things because it's especially if you have data that's not super clean. So if you know what format your data is in, you can actually feed that into Pandas and you can tell it this is the format that my time series data is in. Put this into a time object for me when you're importing this. Okay? And it will happily do that for you. So we've done that. Now I need to actually run it. And we can see that our first 5 rows, which you can access with .head, and you can access any number of rows with .head. You do 10. Our first 10 rows have our now time information, but you can see that it's added a date. So it's basically converted our month, year information to a time object. So now there's a day, there's a month, there's a year. And now we can work with that. So for the other 2 spreadsheets, we do the same thing. So there's CO2 levels.csv, we do basically the same thing, and precipitation.csv, which was the Amazon rainforest. What are we trying to do? I guess I'm trying to see if there's a relationship between how much milk cows are producing and greenhouse effects. I happened to find 3 files that had the same time information in them that I could work with in order to show you this example, but just, for the sake of argument. So now we have these 3 separate data frames that we've just imported from our CSV files. We have our milk, we have our carbon dioxide levels, and we have our precipitation levels. So how do we put that all together into something that we can work with? You could do .merge, which is a common example that you'll find online. And in order to do that with 3 specific data frames, you would have to do .merge, milk.merge CO2, blah, 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 .merge precipitation. So it's kind of messy. The other way you could do that is you could do .join, so milk.join, and then you could specify a list of objects, which is a nice little trick. And the other difference between these 2 commands is that if you notice in the first, in .merge, you have to explicitly specify, use the indices in order to perform the join. So we're basically joining on the time information that we have. And we're doing an inner join here because we may not have the same time information across all of these things. In the second command, you don't have to do that. The default is that it would do a join on indices. And so now we have a import things. Great. All right, now we have a data frame that has 3 columns that have all the information that we need, and it has all of our time series data nicely labeled. Awesome. Okay, so this is the side note about appends. You might have data that comes at you in pieces, and you might have data that comes at you row by row. That happens sometimes. We try to avoid it, but you might be tempted to construct a data frame in a for loop, because you might say, well, there's a append function, and a data frame is basically kind of like an array. It's kind of like a dictionary, so I could just append to this. But what happens is that gets really, really slow. I once tried to do that in a really messy bit of code, and the code took 20 minutes to run. When I put things into a dictionary and then converted to Pandas object, it took 2 seconds to run. The reason for that is that when you, like I said earlier, when you perform any operations like joins, merges, appends, Pandas not only reindexes everything, but it also looks at the types of information that are in each of your columns, and it tries to figure out what type of column it should be each and every time you do that. So let's say you do an append every row, it's going to check every row and every column and see, oh, have you added anything here that doesn't match the column type that I've already specified? So if I suddenly introduce a missing value or a text field, it's going to turn it from a numerical object into an object, for example. And it's going to keep checking that, and that's why it's really, really slow. So you really want to vectorize your operations as much as possible when you're working in Pandas. Okay, and if you must do it, here's an example of how to do it. So, okay, back to our environment example. Let's do a sanity check. Are all the data types that we have what we expect, now that we know that Pandas does this thing where it infers things for us? And in this case, it's actually not true. So our milk is an integer, which we expect because it was 3 digits. Our CO2 levels are an object for some reason, and our precipitation is a float, which is also correct. It was a number less than 1, as I remember. So let's see what's going on here. One of these is not exactly what we want. Hey, cute things. I promised you cute pictures, so there you go. All right, so we can fix that CO2 column, and all we have to do is just specify as type, and you can turn it into something else. So you would basically write that back into the column, and now if we do d types, it all looks correct. Yay! We can also double check that our index is correctly interpreted as a datetime type object by just doing .index, and that's going to spit out everything here. So we can see that our data starts from 1965 January and goes all the way to 1972 December because we did an inner join. Cool. Okay, let's try to visualize it. I did .plot and I got a really pretty graph. No options. Look, Ma, no hands. All right, that's kind of fun. You can't do a lot with it without having to dig into things like matplotlib, but the good news is that you can. So even though the plot functionality in Pandas is somewhat limited, if you look through the documentation, you can actually manipulate it by passing it matplotlib commands. And there's plenty of examples of how to do that, depending on what you want to try to do. So it's actually just basic wrappers for matplotlib under the hood. Okay? So if we look at our data here, we can see that things are on very different scales, and this is not very useful, and this is not very easy to interpret. So, okay, let's try to standardize that data. The nice thing about Pandas is that, again, this is really easy to do. Everything is vectorized. So remember, our data frame is greenhouse. So I could do greenhouse minus greenhouse.mean, and it will know that I want to take the mean of each column rather than the mean of the entire data frame, and that I want to divide that by the standard deviation of each column. Okay, so it's pretty smart about things like that. So now I have a standardized data frame, greenhouse underscore standardize, that I can plot things with. Again, no options necessary. And that produces a pretty descriptive, although not very pretty plot. And now we can see that something weird is going on. For some reason, our production of milk per cow, not overall, per cow, is intimately connected with our CO2 levels, which is kind of interesting. So let's say I wanted to pull out that information, and I wanted to kind of discard the precipitation information for now. Really easy to do. You can just specify double square brackets and your column names. Double square brackets because first square bracket is what you would normally do to specify a column. Second bracket, your list of columns, right? So that's why it looks the way that it does. And now we have a really pretty plot that shows us a very scary correlation between these two somewhat different variables. So let's say we can also see that there's some seasonality in here. Clearly, there's an upward trend, but there's also something going on every year. So let's say we wanted to aggregate that, and we wanted to just look at yearly statistics over time. Again, really easy, because we have time series data that we've just fed into Pandas. You could do .group by, and I'm going to talk about group by in a second a little bit more, and you can feed it a time grouper object. And you can tell it, I want to do 12 months. I want to do 6 months. And in fact, I haven't been running my code, so this probably wouldn't work. Yep. Da-da-da. Yeah, okay. Great, that works. Plot still works. Da-da-da. All right. So I could do 6 months, and it would look somewhat different. You could do 1 month, and that would bring me back to where I was. That's really handy. And there's a dot mean over here that basically aggregates things over those 12 months. And again, we do dot plots. We're just chaining all of these things together, and we have pretty much a straight line between these two variables, which is kind of interesting, and we did that in one line. So I think that's really fun. So since this is practically a straight line, you might be wondering if there's a correlation between these two variables. And you can do correlations really easily by just doing .core on the entire standardized data frame, and you can specify different kinds of methods. So in this case, we use Pearson correlations. And you'll be able to see a correlation matrix between all these different variables, and CO2 for some reason is very strongly correlated with milk production per cow. If you wanted to do significance testing of this particular relationship, that's where you have to get outside of Pandas and you have to use a different library. So in this case, you have to use things like SciPy and you have to import something else, and then you would do Pearson R between milk and CO2, and you would get basically the same number, but then you get a statistically significant or not value. So in this case, our p-values are really, really low, so there's a pretty good chance that there's a statistically significant difference between, that this is a significant relationship between these two variables. All right, so how are we doing? Are we good so far? Are we okay for one more example? Okay, all right. So let's talk about what that group by thing was in a different example with slightly more complex data. You might be familiar with this. This is the Titanic data set, and the error message is there for a reason. And you probably have done this every time whenever you've started like a Kaggle competition or something. This is basically the Kaggle tutorial data set, Titanic Train. So you might be intimately familiar with this, and that's kind of intentional. So what we're doing here is we're just importing this really easily, and we're setting passenger ID as a column as our index. We're not doing anything complex here. There's no time series data to worry about. And then we do describe. And Pandas throws an error because it says, it says an invalid value is encountered in the percentile. What does that mean? That means that it's inferred that the column age should be a numeric column, and it's tried to compute 25th, 50 percentile, 75 percentiles, and it can't because there's missing values. So, okay. Luckily, this is very easy to do in Pandas, but let's just impute some missing values into this thing. All we do is we take the column that we've just imported, Titanic age. We do .fill_NA, and again, we take the mean of that column, Titanic age, and we just throw it in there. And now if we do describe, it works. Now we get everything that we need. So one-line solution for imputing missing data, which has been very painful if you use things like SPSS. Yeah, and you can see that now the data type of this column is float. Before that, it was still float, but had missing values in it. I don't know why I said that. Okay, so here's where group by gets really interesting. If you wanted to compare values of things across different groups, there's a variety of different ways of doing that. Some people prefer to visualize. I like to see averages of things. And in this case, because in our data, we have the probability that someone has survived or didn't survive on the Titanic, and we have a bunch of different properties about that person. And the challenge, at least on Kaggle, is to figure out whether you can predict who survived or who didn't. Now, who has seen the movie? Okay, so you know what happens. And if you haven't, I'm sorry. You probably have been watching spoilers for the last 20 years. I apologize. There are going to be spoilers in this presentation. So we know that a bunch of things happen. There's not enough lifeboats, and so the way that people are selected to be put on the lifeboats is very specific to demographics. Children go first, women go first, and there's probably some class issues as well because this was a long time ago and there were people with different more expensive, less expensive tickets, first class people, Rose with her really big shiny sapphire thing. Yeah, so if we wanted to see to what extent that's actually true in the survivability of this data set that we have, we could really easily approximate that with just group by alone. So let's see. Let's say we wanted to see if there was a difference across the survivability of men or women on the Titanic. And because the value is from 0 to 1, if you take the average of that, you basically get a probability, right? The likelihood that something has happened. So in this case, 74% chance that if you're a female, you survived. If you are a male, it's like a 20% chance that you had survived. And how the group by object works is specify group by, and then you tell it what column you want to group by, and then in this case, we add survive because we only want to know this statistic across the survived column. We could remove that and see what happens. If we remove that, we get this statistic across all the different variables that we have. So it's basically the average of everything. But we're just interested in whether someone has survived. So I'm going to put that back. All right, cool. We can also look at multiple things at the same time. So we know that gender and class are probably important variables, whether someone was a first class passenger or not. And you can just throw that in there. Class is 1, 2, 3, gender is female or male. And now we get some more robust and interesting bits of information. If you were female and you were first class, you have a 96% chance of survival. Actually 97 if you round it up. If you were male and in the third class, you had a 14% chance of survival. Yeah. I know, right? Now, notice that this group by object is actually looks a lot like a series object. It just has a bunch of different things going on with indices. So this is exactly like a series object that you've just seen before. This has multiple indexes, but it's also a series object. So if you try to manipulate it, if you try to work with any of that information in that column, you have to remember that this is a series object. It's not actually a data frame. You can undo that indexing, and I'm going to show you how in a second. But that was one of the things where it took me a long time to figure out why I couldn't access this information really readily when I started working with group by. So this is, for those of you who are familiar with Excel, this is also the same as doing pivot underscore table and throwing a bunch of different things at it. So you're basically approximating a pivot table if you're doing this. Cool. So let's say I wanted to know, I also know that children were a priority, but I have age. So I have like this interval level variable, and I only really care whether someone was above 18 or below 18 in order to make my approximations. How do I transform that data and that age column into something that I can work with? Basically, I want to know if someone is a child, yes or no. There's a couple of different ways of doing that. The pure Pandas way, or the Pandorable way, I saw that in a forum before, I thought that was adorable. The Pandorable way is to do this. This is basically list comprehensions, right? If your age in the column Titanic age is less than 18, put Y, otherwise put N, and we create a new column called Titanic child, and that's it. That's all you need to do. Or, if you prefer, you could do where, which is also fairly intuitive, but then you have to utilize numpy, so you have to import numpy for that. And then you could do numpy.where, and you could say Titanic age less than 18, and you could do, again, either yes or no. So you would find the second example pretty commonly online, but you can also do the first if you really want to be pure Pandorable. I just wanted to have an excuse to say that more often. All right, so now I have 3 things that I can group by. I have 3 things that I think are relevant: gender, whether or not someone's a child, and their class. And now, if I look at that, and I'm going to zoom in because this is interesting. Yeah, that works. Much better, right? Okay, now you can actually see numbers. Okay, so now I can see that if I'm a girl, or if I'm a woman, and I'm a child, and I'm in first class, I have like about an 88% chance of survival. If I'm a woman and I'm not a child in first class, I have a higher chance of survival, which is really interesting. But overall, children have a higher chance of survival than adults, and those in first class have a higher chance of survival than not. And there is a bunch of interrelationships going on here, which are really, really interesting. So if you are a adult male in the first or second class, your chances of survival go to like 10% or below. Sorry, second or third class. Did I say first or second? Yeah. Second and third class, yeah. So basically, if you're not a first class passenger, and you're a guy, and you're not a kid, you're kind of doomed, right? And this is what we know from the movie, but now we can see that in a nice, handy format. And now we have like this 3-level gargantuan thing with a bunch of columns that we don't really understand. So what you can also do is you can tell it to not use an index. And that group by object is going to spit out a data frame instead, which may or may not be useful depending on what you're trying to do. So I, for instance, when I first ran this, didn't like the fact that child came up N first and yes second, because my hypothesis suggests that it should, I want to look at children first, so I might want to sort this data in some way. I could do that before I do the group by, or I could do that after, because I can take away the index, and then I can perform all kinds of manipulations on this any way I want to, and then I can put it all back together again. I'm going to show you how to do that. So the only thing different here is that I added as index false, and this magically transformed into a regular Pandas data frame from a group by object. So now this is multi-dimensional data. Now there's an index from 0 to 11, and I can sort by any one of those things. So let's say, cool. Let's say I want to sort first by gender, then whether or not you're a child, and then by class. And I want to do that in different ways. So some are going to be ascending, some are going to be descending, because I want to arrange the data in a particular way. Sort underscore values by this thing, and if you want to see this thing, you can look at the slides more carefully later. All this is easily Googleable, and there we go. I've just sorted that information into something that helps me. So now I know if all the women go first, then whether or not you're a child, then your class. And that helps me interpret the information. So, okay, how do I put this back into a group by object, the one that I saw? This is where the multi-indexing comes in. So you might have seen this in the documentation and you're like, what are multiple indexes and when do I need them? And am I ever going to use them? It turns out that group by actually uses multiple indexes in order to present all this information to you. So here's roughly how it works. Okay. Took me a while to wrap my head around this. So I have a series of lists here, which I called iterables, for those of you who can't see the text because it's a little small. And they're basically options in my data. Male, female, yes, no for children, 1, 2, 3 for the class. And what I would do here is I would first construct the multiple index from a product of the iterables, and then I give it column names, which is gender, child, and class. And then I do set index, and I feed it this index object, and that's it. All right. So it does this weird thing where now there's a whole bunch of things here that I don't need. I could do dot survive and get myself back to that group by object that I wanted. So multiple indices are not exactly the same thing as group by, but what, as I understand it, is happening here is that multiple indices allow you to specify combinations of things provided that they already exist in the data. It's not going to do aggregation for you. Okay, so if you just try to throw a multiple index on our original Titanic data set and say, okay, I want to index by gender, whether or not, someone's age, and I want to index by class, it's not going to let you do that. Because it's going to say, well, I don't actually have a value for all of those 3 things at the same time. You have to compute that first. So if you have data that is multidimensional in that way, where you have a value for a bunch of different things, then you can use multiple indices in order to access that more easily, which is where group by works, because it does that calculation for you. It does that averaging, and it says, okay, these are the averages for this thing. If you are female and you are a child and you are first class, this is the number. Then you can put that into a multiple index, and that's why we can convert from one to the other. Does that kind of make sense? Okay. This is the hardest thing I will show you, I promise. All right. Finally, really finally, okay, visualizing the relationship between these 3 things. So you might have guessed that there's interaction going on here. And interactions are notoriously difficult to plot in any graphing, any statistical language of any sort. I use Excel spreadsheets, I will admit freely. They're very handy. I can show them to you later. But then I found Seaborn, and it's pretty. So let's try Seaborn instead. All right, we're going to import Seaborn, and I'm going to do this really pretty plot. So what I'm doing here is I'm saying, okay, I want to plot the likelihood that someone survived, which is on my y-axis here. I'm going to plot the class along the x-axis, so 1, 2, 3, and I'm going to separate children and non-children, and I'm going to colorize different lines by gender, and that will draw me an interaction plot, which is amazing, and I've been waiting for this my whole life, pretty much. Okay, and the nice thing about Seaborn is that it expects a pandas object and it knows what to do with a pandas object, so you could just throw a Titanic data frame into this. And you can say data equals Titanic, which is the thing that we had, and you can give it all the column names, and you can even give it different colors, which is what I do here. So, this is just a color palette, and it's a dictionary composed of HTML colors, so you don't even have to worry about that. You could do a scatter plot if you wanted to, and I tell it to use a logistic regression because survival is 0 to 1. Okay, so if I run that, I can also set x and y limits in basically one line. I can say, okay, let's say my x is my class, so I know that it's 1, 2, or 3. So I set my x limit to be 1 or 3. I set the ticks to be 1, 2, 3, and I set my y limit to be 0 to 1 because I know that there are no values that are outside of that. And that for me was kind of a life changer because I've spent so much time wrangling with this in various different kinds of graphical tools. Okay. This one takes a while. Let's just wait for it and stare awkwardly at each other. And the reason it does that is because it's also calculating the confidence intervals. So as much as Pandas is fast, Seaborn is not when it's calculating confidence intervals. It's pretty though. You can turn those off. So if you want to do anything that doesn't require you waiting 10 to 18 seconds, I actually ran some tests and timed this. This takes about 18 seconds to run, which is really long for anything that you're trying to do. This data set is not that big. Turn off confidence intervals and it will get a lot faster. Doo-doo-doo. Yay! All right, something like that. Yeah. I'm not sure why that's so far down, but there you go. Okay, so it's pretty. And now you can see that thing that we had seen in the group by object, which is that if you are a child and you're in first class, or if you are a woman in first class, you basically got in, you're fine, right? But as your class goes up, the likelihood of your survival goes down regardless of whether or not you are in one of those demographics. So if you're in third class, basically there's not a lot of hope for you. And that's a really nice way of visualizing interactions between different kinds of variables. So I was really happy when I found this. Okay, so one last thing that we can do. I found it a little bit counterintuitive to try and plug all of this into a regression model so I can actually look at some of these coefficients, because Seaborn is not going to let you do that. It's just going to make pretty pictures. It's not actually, I couldn't figure out how to extract data from it. Maybe you know how to do that, let me know, because that would be awesome. But instead I had to use SM and stats model, and there's this thing called Patsy, which is great because it allows you to write regressions the way that you would expect to in R. All right, so it looks kind of like this. We do, for some reason, we have to construct our Y and our X objects separately with Patsy, but that's fine. So we do this thing, we run D matrices, and then we give it what we might expect in a regression. So this is our outcome variable survived. We have that nice little tilde that we're used to from R. We have our variable gender. And what I'm doing here is I'm basically selecting the treatment. So I want to know my reference column because all of this is categorical data. Gender is categorical, my class is categorical, and so is my child status, whether or not you're a child. So if you plug that into a regression, what's going to happen is that usually the thing that you're using, the thing that you're calculating with is going to decide a reference point for you. And it's going to say, it's going to give you approximations with reference to a particular group. So you can select that group using this thing. And then, again, this expects a Pandas object, Pandas data frame very easily. You can just throw Titanic in there and you can use column names. You don't have to do anything in particular special. And you can tell it to return a data frame, which is also nice. So then you do your regular linear, ordinary least squares regression, do a fit, and we can extract some values from that. So here's our model fit is not fantastic. We're explaining about 40% of the variance in survivability. And all we did was we basically put those three things together, those three variables. We can include interactions in the way that you usually would, which is to use a multiplication instead of a plus, and that's going to calculate interactions between all the different levels of our variables. Ooh, lots more stuff. And our model fit has improved a little bit. Right now it's about 43% as opposed to 38% what it was before. And you can extract easy statistics from this in the way that you would normally work. So you can extract the R squared itself. You can extract the p-values, which are all over here. And this is what I mean by reference group. So this value says that if you are a woman, you have a statistically significantly, your chance of survival is statistically significantly to be more likely than if you're a man in this particular regression. And then when you look at the interactions, it gets a little bit more complicated in terms of interpretation because it's categorical data. But it's basically saying, okay, let's take a reference group here. So compared to males, Women in the first class will have a statistically significantly more likely chance to survive than men of the same class, and all kinds of different things. So you can use your regression to tell you a lot more specific things. And when you're doing predictive modeling, this is basically what's happening under the hood. It's basically calculating all those things, and it's determining probability of success based on a number of different characteristics, and it's feeding that back into a model. And if you want to know more about how that works, ask me questions about this later. I'll be happy to talk to you more about the statistics behind this, because it's really fun. Yeah, and we can also turn this into likelihood. So usually your regression will spit out a coefficient, which is not particularly easy to interpret as a human, but you can do a quick manipulation with numpy, basically use an exponent, and it's going to give you a likelihood or odds ratios instead. So in this case, if you're a woman, you had a 1.65 times greater chance of survival than if you're a man. If you were a child, your survival, all other things being equal, so assuming you were of the same gender, assuming you're of the same class, you would have a 1.17 greater likelihood of survival than if you were not. All right. But, you know, this is statistics. This isn't really pandas. Okay, so the last thing, I said that like 3 major slides ago, and you're all still here. That's great. Okay, so for those of you who have been using pandas for a really long time, a new version has just come out, and it does just minor incremental things, but I think they were really cool. You can now specify categorical data with read CSV, so you can tell it that this is a category data type, so you don't have to do that later, and it might save you lots of, it might give a lot of speed improvements. Because the way that this is implemented during import is a lot faster than doing it later on the object. You can also concatenate categorical columns now really easily, union underscore categoricals. You can merge time series by certain date chunks, which is really nice. So you can say merge as of a certain time, and it will do that for you. And the rolling function, which we hadn't really looked at, but it's basically, you know, all kinds of cumulative statistics, is now time series aware, and it supports an on parameter. So you can tell it, oh, give me like rolling means across 12 months on this column that is not an index, and it can now do that for you. All right, cool. Now you know Kung Fu. Go forth and pandas. And that's it. Thank you. If you've done something differently, I'd love to know. So, I'm learning too. Questions? No? Cool. That's either a really good sign or a really bad sign. Yes?
What's the biggest data set?
The biggest data set? That's actually the one that I started with. This was a dump from Wikipedia of all of the conversations in a certain subsection of Wikipedia over the last 4 years. So I was working with, hundreds of megabytes worth. Not that huge, but it was enough for me to start thinking about not using for loops. Yeah.
How did you get that data? How did you get the data?
I asked them for it. They're very nice about that. As long as you publish things that you do, but I'm on a live stream. You should basically just go to Wikipedia, and there's lots of ways that you can interact with wiki data, which is really cool, and I can talk to you more about it afterwards too.
Forgive my ignorance on this bit, but what's the difference on the time comparisons between the different types of joins? What is the difference between outer, left, and right? As I'm familiar with left outer joins in SQL, but
as opposed to outer and inner?
as opposed to left, right, and outer. What distinguishes those three?
I'm not sure I understand what you mean.
You can talk about it later on.
Please do. I want to know more. Does anyone else have any other questions? Yay, okay, thank you. You can all go home now.
Okay. All right. Thank you guys. Thank you, Anna. That was awesome. So, as is typical for presentations at Google, we're probably